Okay, so the point of that exercise on Desmos with the guessing on a quiz was this. You're supposed to recognize that the number correct, if we're using or guessing on 4 questions, could be 0, 1, 2, 3, or 4. Basically, our traditional that we're going to see a lot, none, up to all, right? So 0 all the way through whatever our n is. These are all the possible outcomes. This is the sample space. And the probability for each of these things, well, as we're going to be moving forward, we have 4 things that we're essentially randomly selecting. And each question has 5 options. If they're multiple choice and you're just guessing, that makes the probability of getting, oops, can you see this? Getting this question right or correct equal to 1 out of 5 or 20%. So that also means we know the complement of getting the question right or the probability of getting it wrong is going to be 4 out of 5 or 80%, right? Because those things have to be complements. It's either one or the other. So we're going to use that 1 minus to find the complement. All right, so we have to figure out the probability for each of these. Remembering that we are doing this for 4 questions. So even when the person gets 0 correct, we still need to have 4 different things happen because there's 4 questions. So each of these are going to have those 4 different possibilities, right? Those 4 different random events where the student either gets the question correct or incorrect. So for the first one, if they get none of the questions correct, that means every single question was wrong. Sadness. And then we can look at each question individually, right? Because these are independent events because the student is just guessing. There's no impact, right? If you think about the questions, the answer choices A, B, C, D, E. As we move to question 2, the answer choices are still going to be A, B, C, D, E. Even if we randomly guessed and chose E on the first question or C, doesn't matter. The answers are still all there. So this can be thought of as sampling with replacement because theoretically, we're going to have the same 5 answer choices, right? Not theoretically, but actually we'll have the same 5 answer choices on every single question. So sampling with replacement, which means we have this independence as we move from one to the next. So the probability that the person gets the first one wrong, oops, I want to choose my red, is 0.8. Second one is still 0.8. Third one is still 0.8. And the last one is also 0.8. I'm not going to calculate this now because I'm just trying to show us what the whole point of that entire exercise was. So the second one, they get one of the questions correct. And so I am an impatient person, so I tend to make sure that the correct or the right answer happens first. Now, if I'm smart, I remember, oh, this is that exactly one that we had back in sampling with replacement. This is the one where I needed to be clever and multiply by the fact that I could have gotten it correct, wrong, wrong, wrong. Wrong, correct, wrong, wrong, right? I could have gotten any of the questions correct, so it could have happened one of 4 ways. So I'm going to do a 4 out in front. And then all of the wrongs have an 80% still, and all of the corrects, well, that's a 1 out of 5 chance, a 0.2. Again, I'm not going to do the calculation yet. So I'm going to jump to number 4 because 4 is an easier one to deal with than numbers 2. Correct, 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 correct. In this case, there's no other way to order that, right? That's the only way this magical thing could happen, which is 0.2 times itself 4 times. And then I'll do 3. In 3, there's only 1 wrong, so again, that could happen 4 different ways. So this is going to look like this. Oops, I wanted my green. Ooh, I wanted that to be red. Guys, I have all these goals in mind with color. All right, so there we're looking at what we're doing here. And so the last one, figuring out what needs to happen, that's simple enough. Correct, wrong, wrong. So this will be a 0.2 times a 0.2, and then a 0.8 and a 0.8. And then what you probably had happen if you actually worked through that activity and took it earnestly, even though it was just based on attempt instead of actual correctness, was you probably had the number of ways incorrect in the front. Most students just guess that the number of ways is still 4, but indeed, if you were to write these all out, I'm going to just go ahead and keep the first one correct, and now I'll have to change it. And then there's 6 different ways for this to happen. So that was sort of the magical piece to this. And I only care about the idea that this brings out a pattern, right? We can see this is, and we can see as we're going, and it might be even easier without the exponent notation, that we are increasing the number of 0.2s by 1 each time and decreasing the number of 0.8s by 1 each time. And we can kind of see that happening here. So there's this pattern that's going on in this question. And this is actually a pattern that's true with any sampling with replacement type question. These trials, if they're independent and we're only taking a certain number of a sample, we are always going to end up with this, oops, that was not what I wanted, this pattern going on. And it pattern totally makes sense to me when you think about it. The number of things that we want correct, we need that probability that raised to that power. So our probability of being correct needs to be raised to the number of corrects we wanted. I'll call that a K. And then the probability of being incorrect, we'll just call that 1 minus P, has to be raised to the rest, right? Every other one you had to have gotten incorrect. And then you've got to deal with the number of ways out in front. So this is the general formula for whenever we're, oops, you guys can't see it, the general formula for whenever we're dealing with sampling with replacement. And that actually brings us to a beautiful thing. This is the binomial distribution, and this is where we're going to be starting next class with tomorrow, is this idea of the binomial. So as long as we have these certain things, B being binary outcomes, so in our example, this was that they could have gotten the question correct or wrong, right? So those were the only 2 outcomes. One thing that we do want to make sure is we're counting up successes. I kind of brushed past that idea. So in this case, we were saying how many questions did this person get right? Independent, this is the idea that the outcome on one trial doesn't influence the next. So if I guess right on number 1, that doesn't change anything about number 2 since I was just guessing. So that's what would have gotten us independence here, was the idea that we were just guessing. So there was no probabilities changing. We do need to have a fixed number of trials. So there are, situations where maybe you could keep going until you got an answer wrong. That would not be a fixed number of trials because you wouldn't know how many questions he would see. So in this case, we did have a fixed number of trials. We had, n is equal to 4, right? There were 4 different questions he was guessing on, didn't change anything. And the last one here is a little bit funky. The probability of success has to be the same for every trial. So on my test questions, right, I don't necessarily always have 4 or 5 answer choices. It sort of depends on the question, whether it really, sometimes it's obvious that there should just be 4. Sometimes a 5th one is makes sense. So you couldn't use this on mine. But in this particular example, our probability of success was that 1 out of 5 because every question had 5 answer choices. So that was always the same for every single thing. If that's all true, then we can say, sure enough, yes, the number of successes follows a binomial. And we even have cute notation for that. It's later on the page, but I'll just write it here. In this case, X, the number of correct answers, would follow a binomial, and we use this big capital B to say it's a binomial distribution. It's just shorthand with 4 trials and a probability of success of 0.2. This is just mathematical shorthand telling somebody you can make that entire beautiful table up above without anything else. I don't need the whole word problem. This tells me everything I need to know. So we're going to jump in and play with the formula, which is later here on the page. This idea of n choose k, which is our number of ways. I keep going off the page. I keep forgetting that we could order those successes. Our p times k, which is the number of successes times that probability raised to that power, and then our q to the n minus k, which is our failures. So we could go ahead and even use this on, say, that one question that we all had trouble with, and that's what we'll start next class with.